So last time we were talking about haloalkanes one, like haloalkane one. Now we move on to haloalkanes two. And the first part we have done this thing and this thing. Now we move on to, and we talked also about the physical properties. Now we move on to the chemical properties. Now, before you move on to the reactions, there are few important things to understand that makes it easier for us to understand why a specific reaction is taking place and why it follows a specific way of, that means the mechanism. The first thing you need to understand is that when you're talking about haloalkanes, they have this thing. You have a carbon which is attached to any other carbon and one halogen atom. This will be partially negative, this will be partially positive. So we know that this bond is, that means the CX bond is polar. That's the first information we get, that this is a polar bond. Another important thing is that over here there will be some other group that will come and attack it, and in this way this will be removed out. So basically the X will be replaced by, now replaced by what? So something that attacks the less electron density center or low electron density center, that is called as a nucleophile. That is, so the X will be replaced by a nucleophile. Now here two words important. The first word is it is replaced and the second word is nucleophile. So therefore you can say that the reactions of haloalkanes, that is the reactions of haloalkane, they follow the mechanism of nucleophilic substitution reaction. Substitution reaction. So if they ask you type of reaction for haloalkane, if they say type of, then you will say nucleophilic substitution reaction. It's usually 2 marks question, where 1 mark will be for the nucleophilic and the other mark will be for substitution. It is similar to when you were talking about reactions in alkanes, it was free radical substitution, and for alkenes it was electrophilic addition. So similar to that, the haloalkanes, they undergo nucleophilic substitution reaction. That is the main reaction. That is the main reaction. Now nucleophilic are 2 types, SN1 and SN2, but this is in A2 level, that is grade 13. So we will not go, it used to be before in an older specification, it used to be there, but now it has been shifted to A2 level. So we will not go into the details of SN1 or SN2, we will just understand that it is a nucleophilic reaction. That is first thing you should know. The second thing before we move on to the reaction which we should know is the relation of the bond strength. That means strength of bond. Now if you look at the strength of bond, you have a carbon fluorine bond. Remember, we are looking at this bond because this is the bond that is going to be broken, carbon and the halogen. Then you have the CCl, which is this thing, and you have a CBr, it is this thing, and then you can say Ci, this. So you have the bond that breaks is the carbon and the halogen bond, so we are focusing on that. Now when the reaction is taking place, it is this bond that is going to break. So that is why we are talking about the strength of the bond. Now we know that fluorine is the most electronegative. This is most electronegative. That means that this bond is most polar, while this bond is the least polar. This bond is least polar. So according to that, what should happen is, since it is most polar, that means they are stretching away That means one of the, like the halogen is taking away the electron towards itself, and the carbon is losing its electron density to the fluorine. So they are moving towards like ionic bond. So moving towards ionic bond means that they want to stay separate, a positive and a negative ion. So in this case, such bonds which are most polar, more polar, they break easily. They break easily. While over here it is least polar, that means the electron density is being shared. They want to stay together. So the bond does not, the bond does not break easily. So based on this understanding, based on the polarization, what we understand is that if it is breaking easily, that means the bond strength should be the least. Bond strength should be the least for this and maximum for this. It should be. However, that's a very common question asked. However, what has been observed is that the CF bond is the strongest bond among the carbon halogen bond, So they will ask us to explain this. Why? So the problem here is, on the basis of the polarities, it should be this. So this is based on polarity. That the bond strength should be the least for the CF. However, experimentally, it has been observed that the CF bond is the strongest bond and the CI bond is the weakest bond. This among the cars. So this is the weakest. So we need to explain that, why that is happening. So the simple reason is, so when you say a strong bond, it means the CF bond to break, the bond enthalpy is greater. The bond enthalpy is greater than the CI bond. That means to break the carbon-fluorine bond, you require more energy compared to the CI bond, even though the polarity is showing us a different thing. The polarity is showing us the opposite, or explains the opposite thing. For this, to understand this, to explain this, you need to take the help of bond lengths. Now, if you look at the bond length, you have the carbon-fluorine, carbon-chlorine bond, carbon-bromine bond, and carbon-iodine bond. Now, we know as you go down the group, the atomic size will increase. So if the atomic size is increasing, definitely the bond length will increase. The bond length increases. Now, bond length increases. Why does the bond length increase? Like, for example, carbon is something which is constant for all of them. Now, fluorine is this big. So the bond length for is this part. This is for CF. So this is your bond length in case of CF. But if you move to the carbon chlorine, carbon is still this size, but the chlorine is becoming bigger now. So the distance between the nucleus is now more. It has increased further. So CCl. Now this is your bond length. So you can observe, as the atomic size of the carbon is a constant atom, it's the same common one. So if you go to the iodine, carbon is here, and iodine is this big. So the distance between the nucleus is still more or furthermore. So what is happening is the bond lengths are increasing. The bond lengths are increasing. So the order of bond length is the order of bond length is the CF is the smallest, then you have the CCl, then you have CBr, and then is your CI. So this has the maximum bond length. Why? Because the iodine atom is the biggest, largest of all the halogens, and therefore breaks easily. Or you can say has less, or I would say least, because we are comparing it with others. This has least bond enthalpy value. You don't need to memorize the exact values. You just need to know that because it has a maximum bond length, so will break easily. As a result, it will have the least bond enthalpy value, while the fluorine one, it has the smallest bond length. As a result, will have the maximum bond enthalpy value, not easy to break, and so the bond does not break easily. So the bond enthalpy value is less. That's the important thing. So actually the breaking of the bond depends. In case of fluorine, in case of the carbon halogen bond, it is more dominantly affected by the bond length instead of the polarization. Otherwise, usually it is the polarization that helps us to know which bond breaks easily or not. This is a very, very common question or comparison that is being asked. Now moving on to the reactions of haloalkanes. So the first one, now the first one is reaction with aqueous NaOH or KOH. Now they can give you anything, NaOH or KOH. The reason is this Na and K, these are spectator ions. So whether you have this Na or K, it does not matter. Main thing is the KOH ion. Now here an important thing is that it is the OH minus that will replace the halogen, that is the X, and alcohol will be formed, and then the reaction condition, if they ask you, then you need to simply say aqueous condition, that means dissolve in water, and then heat under reflux. Now we will talk about heat under reflux a little while later. What is the meaning of that? Now over here, let's talk about this reaction. Now CH3, CH2, and I'm taking a Br over here. So the name for this would be bromoethane. Now when you react it with NaOH, aqueous, now this Na will actually be Na plus aqueous in the solution and the OH minus aqueous. So this is your nucleophile. This is your nucleophile, and you have a positive and a negative center over here. Now we have talked, this is not a mechanism, we are just talking about what is happening. So over here, the OH minus, as we have talked before, it will go and attack the carbon. The Br, this thing will go out and attach to the sodium. So at the end, what you get is your CH3, CH2. In place of the Br, you have the OH, and the Na plus combines with the Br. You get the NaBr. Now sodium salts are soluble in water, so it is aqueous. You are getting ethanol. So that is what we said, and alcohol is formed. So if you were taking a K, over here, you would have ended with potassium bromide. If instead of a Br, you had a Cl over here, you will have ended up with Cl. So that would be the change. Any number of carbon atoms, any structure, you just combine over here. Just copy and paste. The only place where the reaction is taking place, is your OH is being replaced. So if I take another example just to showcase what is happening, if I have this thing with a KOH aqueous, what will happen is I just copy paste the whole thing, the haloalkane. Instead of the Cl, I will put the OH from here, and the Cl will go to this. So you started with 2-chloropropane. You end up with propane 2-ol. That's the only thing. So we move on to the first reaction was reaction with aqueous NaOH. So the first reaction you did was reaction with the aqueous NaOH, and this is an example of a substitution reaction. Now we move on to the second one, but before that, let me quickly explain you the mechanism of this, because sometimes in your exam they do ask you the mechanism of this. I have already explained you, but the way to show the mechanism, that we will try to understand. So for this reaction, the mechanism would be, like for example, you have a, let us say you had a CH3, you have H over here, or let me keep it over here, this side Cl, just to make it a little more clear, nothing else. And you have a H over here, you can have H over here, you can have a CH3 over here, that doesn't matter. Now the OH minus ion, remember when you are showing the OH minus, it is a nucleophile, it has a lone pair of electron. This will be partially positive. These are the ones that will give you the marks, like the negative charge and the lone pair of electron, then positive and partial positive and negative charges on the carbon Cl bonds. Now what happens is, start the arrow either from the negative or from the lone pair to the carbon. So this is a nucleophile attacking a low electron density center, and then this bond breaks up heterolytically. Carbon Cl is more electronegative, so it takes away the electrons, and you end up with CH3 over here, and in place of the Cl you get the OH, and the Cl minus is left out. Now this will go and combine with the K or the Na with the OH. So if you have a Na over here, it will combine with this to form NaCl and so on. But this is what is required as a mechanism. If they ask you to show the mechanism for aqueous NaOH or KOH, this is the you have to only show. Nothing more. That explains everything. Now moving on to the next reaction. That is reaction with alcoholic NaOH or KOH. Now, I'm using the word NaOH, alcoholic or NaOH or KOH. In your exam, they may use the word ethanolic. So ethanolic means dissolved in ethanol. I'm using the word just alcohol, so it could be any alcohol. But what we specifically mean over here is that if you are taking NaOH or KOH, they are being dissolved in alcohol. It could be any alcohol. In your exam, sometimes they specify ethanol. So, okay, it is dissolved in ethane, nothing else. So over here, the important thing is that this is an example of elimination reaction. So in elimination reaction, nothing is being substituted, everything is being removed. That's very important thing. This is an elimination reaction. So when you do the reaction with alcoholic NaOH or KOH, so the solvent is very important, alcoholic. So in that case, elimination reaction takes place. You have the alkene is formed. So not an alcohol, alkene is formed. That means a double bond is formed. And an important thing, very commonly asked question, that OH is over here is behaving as a base. In the previous case, it was behaving as a nucleophile. So you were calling it as an nucleophilic reaction. So this was an example of this reaction was an example of a nucleophilic reaction. This is a nucleophilic reaction example. And the OH minus was the behaving as a nucleophile over here. While in this reaction, the OH minus is behaving as a base. So over here, let us say, just for the sake of making it a little more clear, I'm writing the H over here, and you have a CHBr over here. So you have a haloalkane. This is 2 carbon atoms. So this is bromo ethane. And now when you react it with NaOH, alcoholic or ethanolic, what happens is these two atoms, they take away their electrons. They take away their electrons out. This is not a mechanism. I will show you what happens. And the electrons which are left over here, they come over here. So this is not a mechanism. This is just I'm trying to show how it is formed, just to remember it. So what will happen is the CH2, double bond CH2 will be formed because the green arrows, they bring their electrons common. Before, the electron of this carbon was shared with hydrogen. The electron of this carbon was shared with the bromine. Now they break away from the hydrogen and bromine and they share among themselves. And the H combines with the OH, forming water. And the Br combines with the Na and forms NaBr. So you have your alkene form. You can call it is ethene. So you start with bromoethane, you end up with ethene. So this is an elimination reaction. Why? Because over here, H and Br atoms are eliminated. So these two are eliminated. So we could take any example. Let's take another example. Now, if I take it like this, let us say I have a H over here, I have a Br over here, I have let us say CH2, and then, okay, let me keep it this way. To make it only little more clear and understandable, that is what I'm doing here, writing the H this way to show that these are the ones that can break. and then you are reacting it with KOH alcoholic. In this case, what happens is there are two choices. There are basically two products which can be formed. There can be two products which can be formed. So over here, what happens is when it reacts with a KOH, definitely the Br will take away its electron out. Now, if this H takes away its electron, so these electrons will come over here. Remember, this is not the mechanism. So this will end up with, you will get the product as CH2 double bond CH, CH2, CH3. So you will end up with but 1-ene as the major substance. But if instead of this hydrogen goes out, so what will happen is the electrons will come over here. The electrons will come over here, and you will end up with CH3. This remains unaffected. This will be CH, but the double bond will be formed between this. So now you will end up with but 2-ene. So you will end up with this plus the KBr plus water, and over here you will end up with KBr plus H2O. So the difference is you get 1 but and 2 b. So you will be getting a mixture of products. So you need to be careful what reactants are given to you, because that will decide what will be formed, one product or two products. One products or two products. Here also, if they ask you the reaction condition, just say reaction condition, you just say reflux in alcoholic solutions. Finish. That means dissolve in alcohol. So I hope this is clear. And if I want to show you the mechanism, then over here, let us say you had a CH3H and you have a Br over here and H over here. So what will happen over here? Now we said that the OH minus behaves. The important thing over here is that the OH minus is behaving as a base. Base means it accepts the H plus ion. It accepts the H plus ions over here. So what happens over here is, if you have the OH minus ion, from any source, KOH or NaOH, any source, we know that this is partially positive, this is partially negative, this is partially positive and negative. So what happens is the Br will take away its electron because it is more electronegative. So it will take away the electron from here. And okay, I need to, so the adjacent hydrogen atom over here, I should write it this way. That will help us to understand it a little more. This is CH2, and let us say I write the H over here. So what happens is, then this, okay, again I need to write it to make it a little more clear. I will write it this way, H2, and this is H over here. So this goes over here. The electron from this point will come over here. Now this H is attacked by the OH minus. This H is attacked by the OH minus. So, and the electron from here shifts to this, or this is wrong. Why this is wrong? The reason is the Br is taking away both the electrons. And this bond shifts over here. So you end up with H2C double bond CH, H, and the Br separates out. The H, it combines with the OH minus to form the water molecule. form the water molecule. So that is the mechanism. So Br takes away, so you can easily observe over here that the OH minus accepts the or takes away the H plus ion. So that is why we say the OH minus behaves as a base. So that's the difference between these two reactions. That is the difference between these two reactions. Now, if you want to compare these two, like if you have a reaction of haloalkane, with aqueous NaOH or KOH, or okay, plus water over here, or you say alcoholic NaOH or KOH. Now, haloalkane, when it reacts with this, the first major difference between them is that this is a nucleophilic substitution reaction, while this is elimination reaction. In this case, alcohol is formed. In this case, alkene formed. In this case, the OH minus acts as a nucleophile, so it attacks the carbon which is positively charged, and over here the OH minus acts as a base, so it takes away the H plus. Base over here means it is a proton acceptor.